Hello everyone, today we are going to study slope deflection method. In this lecture we are going to derive the slope deflection equation. This method is used to find out the reactions of indeterminate beam or frame with rigid joints. What is meant by indeterminate beam? The beam which is having more than 3 unknown reactions is called indeterminate beam. Means we cannot find out the unknown reaction by using 3 equilibrium equations. So in that case we have to use some different method to find out the unknown reactions. We can use slope deflection method, we can use matrix method, we can use moment distribution method. But today we are going to study the slope deflection method. Now let us start with the derivation. Now assume a continuous beam over here like it is shown in the diagram and consider a middle portion in between the continuous beam. Let us consider A and B with a simply supported and having a part of a continuous beam. It is loaded with some external load, that is UDL. Now due to UDL it will be deflect in a downward direction in something like this shape. At point A we will have slope theta A, at point B we will have slope theta B, and it may have a deflection delta in the downward direction. And as the beam is continuous one, we will have the fixed end moment at A as m bar AB, fixed end moment at B as m bar B. Now to move ahead, we will assume some sign convention. If the moment is end moment or any moment is clockwise, we are going to consider it as a positive, and if it is anti-clockwise, we are going to consider it as a negative. Same for the slope. If it is clockwise, then consider it as a positive. If anti-clockwise, consider it as a negative. And if we will have a downward deflection, consider it as a positive deflection delta. Now to find out now to derive the equation, step number 1 is we have to assume that span AB as a fixed one, and we have to consider the fixed end moment in the derivation. Due to external loading, it will be deflect in this shape. So we will have the fixed end moment m of AB, A to B, and B to A, it is m bar of B. We are going to denote the fixed end moment as m bar AB and m bar B. The next step is we are going to release the joint A. We have to release the joint A. If we release it, we will have the slope theta A at A, and this is the fixed point, this is the fixed joint B. Due to this slope, it will be subjected to a moment of 4 EI by L theta A at A. And in case of a beam, if one end is fixed and another is free, the half of the moment is transferred to a fixed beam. So half of this will be transferred to this, that is 2 EI by L theta A. Next step number 3. In the previous step, we released joint A. Now in this, we have to release joint B. Now the support A is fixed, and it will be, now we are going to release support B. Due to this slope at theta B, it will be subjected to a moment of 4 EI by L theta B. As I said, the half of the moment will transfer to the next, that is 2 EI by L theta B. Now we consider the fixed end moment also and slope also. Now the next point is we have to consider the deflection at support. Now the supports are fixed, but it still have some deflection or a sinking of a deflection of a support. This is fixed, this is also fixed. We will have this deflection delta. It will be subjected to a moment of a 6 EI by L square into delta, and 100% the deflection will be transferred to a next joint, that is 6 EI by L square into delta. Now the next is we have to add up all the moments at A and B. So cumulatively the diagram is like this: step 1, step 2, step 3 and step 4. Like the final moment M of AB is m bar of AB. This is 4 EI by L theta A. Next 2 EI by L theta B and minus 6 EI by L square into delta. Lastly, we will have the equation m bar of AB plus 2 EI by L common. 2 times theta A theta B minus 3 delta by L. In a similar way at moment for A and B. At B it is m bar of BA 2 EI by L theta A 4 EI by L theta B and 6 EI L square into delta. Finally, we will have this equation. So these two are the slope deflection equations. Now in the next lecture, we will see how to use this equation to solve the indeterminate beam with a different kind of loading. Thank you.